At Arizona State University, we're bringing world-class education from our globally acclaimed faculty to you. Ranked #1 in innovation for 10 consecutive years and #2 among public universities for employability, ASU isn't just ahead of the curve, it's creating new paths to success. Earn your degree from the nation's most innovative university. Online, that's a degree better. Explore more than 300 undergraduate, graduate, and certificate programs at asuonline.asu.edu. With so many options, why choose Arizona State University?
For me, the only online option was ASU because of the quality. Their faculty was really involved with their students and care about your personal journey. The dedication to my personal development from my professors, that's been extremely valuable to me.
Earn your degree from the nation's most innovative university. Online, that's a degree better. Explore more than 300 undergraduate, graduate, and certificate programs at asuonline.asu.edu.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, simulating the universe's first light through cosmic lenses in ancient water around young star. Simulating the universe's first light with SKA-Low. Scientists have developed a highly detailed computer simulation that replicates what the square-kilometer array low-frequency telescope, known as SKA-Low, will be able to observe when it begins searching for some of the faintest and most ancient signals in the universe. This simulation marks a major advancement in the effort to directly study a period of cosmic history known as the Cosmic Dawn, as well as the subsequent Epoch of Reionization, two defining eras in the evolution of the universe. These periods represent the transition from a dark, lightless universe to one filled with the first stars and galaxies. Specifically, the Cosmic Dawn refers to the era about 200 to 600 million years after the Big Bang, when the first stars ignited and began to radiate light into the cold, neutral hydrogen-filled cosmos. Before this, the universe had experienced a prolonged dark age, devoid of any luminous sources. As those early stars began to shine, they triggered the release of a unique signal from the neutral hydrogen gas, a faint radio emission at a wavelength of 21 centimeters. Because the universe has been expanding ever since, this signal has been redshifted to lower frequencies that can now be picked up by sensitive radio telescopes operating today. Following the Cosmic Dawn, the Epoch of Reionization began. During this phase, intense ultraviolet radiation from the first generations of stars and galaxies ionized the surrounding hydrogen gas. This ionization broke the atoms apart and created expanding bubbles of charged particles throughout space. Over time, these bubbles grew and merged, leading to a dramatic transformation of the universe's structure and effectively ending the cosmic dark ages. Capturing and studying these ancient signals is a daunting challenge due to how extraordinarily faint they are. In fact, they are thousands of times weaker than all the foreground noise generated by our own galaxy, other galaxies, and various natural and artificial sources. To properly detect them, telescopes must collect massive amounts of data over long periods, often within specific frequency ranges such as 106 to 196 MHz. The simulation created by Anna Bonaldi and her team at the SKA Observatory in Jadrell Bank, UK, addresses these challenges by including every major factor that SKA-Low will face in real observations. The simulated environment contains not only the actual signal from the cosmic dawn, but also emissions from powerful radio sources inside and outside the telescope's field of view, complex foreground interference from the Milky Way, and the influence of technical limitations such as instrumental calibration issues and atmospheric distortions. All of this is necessary to create a realistic setting in which scientists can develop, test, and refine methods for isolating the genuine cosmological signal from overwhelming foreground contamination. This level of simulation is vital, as it will help astronomers prepare to extract the desired signal from a background filled with brighter, overlapping emissions. The SKA-Low telescope, once completed, will be the most sensitive low-frequency radio telescope ever built. Its extraordinary capabilities will allow researchers to probe the cosmic dawn and epoch of reionization in ways never before possible, offering both high spectral and spatial resolution. The team behind the simulation even included sources with brightness ranging from over 5 Janskis at 150 MHz, which represents very strong radio galaxies, to those a million times fainter, just 1 microjansky, alongside detailed representations of our galaxy's diffuse radio glow and the small structures scattered across interstellar space. The unit Jansky is a standard measure of radio source brightness. When SKA-Low comes online, it is expected to deliver the most accurate and detailed measurements of the first sources of light in the cosmos. In addition to detecting the 21-centimeter hydrogen signal during the early universe, it will also be able to map how hydrogen emissions changed before, during, and after the reionization process. This will provide unprecedented insight into the universe's transition from darkness to light, revealing how the earliest cosmic structures formed and evolved. Through cosmic lenses, unlocking the universe with light and gravity. By combining the way massive galaxies and galaxy clusters warp space and magnify distant regions of the cosmos with cutting-edge instruments capable of detecting both gravitational waves and electromagnetic radiation, scientists are entering a new era of discovery in fundamental physics, cosmology, and astrophysics. A recent study underscores how this approach, known as multi-messenger gravitational lensing, can unlock answers to some of the biggest questions about the universe's structure, history, and underlying laws. These gravitationally lensed explosions, when observed through multiple types of signals, provide an opportunity to see the same cosmic events from different angles, deepening our understanding of phenomena like the formation of compact objects, the nature of dark matter, and the behavior of gravity itself across enormous distances. The research, published in the Philosophical Transactions of the Royal Society A, comes from an international collaboration led by the University of Birmingham. The team acknowledges the technical and logistical hurdles involved, including the difficulty of locating the exact positions of these distant, lensed events and coordinating observations across a wide range of disciplines. They argue that overcoming these challenges will require deeper collaboration between scientific fields, more open data sharing practices, and the development of advanced simulation and analysis tools. According to Professor Graham Smith of the University of Birmingham, recent technological advances have made it possible to observe these cosmic phenomena in unprecedented detail across the full spectrum of energy, from radio waves and visible light to gamma rays and gravitational waves. These improvements set the stage for what could be transformative breakthroughs over the next decade. With these tools, researchers hope to refine our understanding of how quickly the universe is expanding, probe the elusive properties of dark matter, and reveal how extraordinary cosmic events like neutron star collisions and black hole mergers come to be. The core of this new strategy lies in the technique of multi-messenger gravitational lensing, which leverages signals that span an immense range of energies, from high-energy neutrinos to the subtle ripples of spacetime known as gravitational waves. By using massive celestial objects as natural lenses, this technique can amplify and even duplicate signals from faraway events, offering rare opportunities to test gravitational theories and gain sharper insights into the early universe. It also provides an innovative way to connect seemingly unrelated phenomena, like fast radio bursts and gamma-ray bursts, to common origins, giving scientists multiple viewpoints on the same underlying events. Looking ahead, the focus is on what can realistically be achieved in the next 10 years with instruments either currently operating or on the verge of coming online. Key facilities in this effort include the LIGO-Virgo-KAGRA network of gravitational wave detectors, which are already capturing space-time disturbances from cosmic collisions, along with advanced satellite observatories monitoring the universe in gamma and X-ray wavelengths, and cutting-edge radio surveys. Central to this effort is the Vera C. Rubin Observatory, whose legacy survey of space and time, LSST, is set to launch at the end of 2025. Anticipation is building around the observatory's first public demonstration this summer, when the team will unveil initial images captured by the powerful Simone Survey Telescope, an event expected to mark a major milestone in observational astronomy. Professor Smith emphasized that multi-messenger gravitational lensing represents not just a technological advance, but a turning point for the global scientific community. The progress made so far is the result of collaborative efforts across borders and disciplines, with early career researchers playing a key role in shaping this field. This international cooperation is creating fertile ground for the next wave of transformative discoveries. Dr. Gavin Lamb, of Liverpool John Moores University, noted how ideas that were considered fringe or speculative just 5 or 10 years ago are now forming the basis of next-generation scientific inquiry. Helena Ubach, a postgraduate researcher at the University of Barcelona's Institute of Cosmos Sciences, expressed her enthusiasm at being involved in such a dynamic and emerging area, and her excitement about the discoveries that are likely to unfold in the near future as this field rapidly evolves. Ancient water ice found around young stars suggests pre-solar origins. Astronomers from Leiden University in the Netherlands and the National Radio Astronomy Observatory in the US have made a major discovery. For the first time, they've clearly and reliably detected semi-heavy water ice, water that contains deuterium instead of one of its hydrogen atoms, around a young, sun-like star. This is important because it strongly supports the idea that some of the water found in our solar system actually formed long before the Sun or the planets even existed. The team's findings, published in the astrophysical journal Letters, revolve around a key method astronomers use to trace the origins of water, by measuring something called the deuteration ratio. This ratio tells them how much of the water contains deuterium, a heavy version of hydrogen, instead of regular hydrogen. When water contains one deuterium atom, it becomes H2O instead of H2O, and we call it semi-heavy water. A high concentration of this kind of water usually means it formed in extremely cold environments, like the dark, icy clouds of gas and dust that stars are born from. Interestingly, in places like Earth's oceans, comets, and icy moons, about 1 out of every few thousand water molecules is semi-heavy. That's much more than what you'd expect based on the composition of our Sun. So, scientists have theorized that this water must have come from those ancient dark clouds and survived all the way through the birth of our solar system. But to prove that, they needed to measure the deuteration ratio in the solid water ice of young star systems, which, until now, wasn't possible with enough precision. That changed thanks to the James Webb Space Telescope. Using its powerful instruments, the researchers examined a young protostar called L1527 IRS, located about 460 light-years away in the Taurus constellation. This star is thought to resemble what our own Sun may have looked like in its infancy. For the first time, they were able to directly observe a clear signature of semi-heavy water ice surrounding this baby star. What they found is that the ratio of semi-heavy to normal water ice around L1527 is quite similar to what we see in some comets and in other young star systems. This suggests that the water in all of these different places may have a shared origin, one that goes all the way back to the cold, dark clouds from which stars form. According to Wijn van Dishoek, a senior astronomer at Leiden University, this adds to the growing body of evidence that most of the water ice in space travels through the entire star formation process without being significantly changed. Still, there were some small differences in the water ratios. For instance, the semi-heavy water ratio in L1527 is a little higher than what's been measured in comets and on Earth. That could be due to a number of reasons. Maybe some of the water in our solar system was chemically altered as it moved through the protoplanetary disk, or maybe the dark cloud that formed our Sun had slightly different conditions than the one around L1527. To better understand this, the team plans to continue their observations. They're now preparing to look for semi-heavy water ice in 30 other young stars and dark clouds using the James Webb Telescope. Meanwhile, additional observations will be done using the Atacama Large Millimeter/Submillimeter Array, ALMA, this time focusing on semi-heavy water in gas form. Together, these studies could help scientists learn even more about how water forms, survives, and moves through space to eventually end up on planets like Earth.
Ready to make a real impact every day? Join the Active Day Home Care team and help clients maintain their independence in the comfort of their own homes. Make a difference in someone's life as you provide essential daily assistance and protect their health and happiness. Earn up to $20 an hour and enjoy additional perks like optional daily pay, 401k, paid time off, ongoing educational training, and more. Join a team that values care, compassion, and your professional growth. Visit activeday.com to apply.